How about that? There we go. All right. This is the art of defiling, defeating forensic analysis on Unix file systems. Basically, this is the format for this talk. We're going to basically have a brief introduction. Then we're going to go over the background information that you're going to need to know in order to understand the rest of the talk, the attacks and so forth. So we're going to do an overview of Unix file systems. Then we're going to look at forensic analysis from the point of view of an anti-forensic attacker. Then we're going to get to the fun stuff, which is the actual anti-forensic attacks themselves. We're going to skip the demonstration because they're actually on my other laptop, and there's a Q&A session afterwards. If you have any questions during the talk, feel free to ask them. Okay. I'm grugq. Not much more to say about that. Basically, I used to work for a company doing host intrusion prevention systems, but as of last Monday, I no longer do that. So I now spend most of my time doing what I like to do for fun, which is breaking forensics tools, which is essentially an area of the security research which isn't done enough of. There's people breaking all sorts of other applications, but very, very little work is actually applied to looking at the end game of security, which is at the actual forensic side. People usually ask me why I do something like anti-forensics, which many view as being quite hostile to the police or the government forces. Essentially, if you look at security, it's an arms race. Every time one side makes an advance, the other side tries to do something to compensate and mitigate that advance. So these days there seems to be quite a lot of post-intrusion analysis. There's starting to be a lot of forensics analysis that's being done once someone has broken in. And as a result, more and more hackers are starting to use anti-forensic attacks to make sure that when someone does discover an intrusion, they're not backtracked and found out. So basically, the hackers are doing this. This is one of the few venues where you get to find out what the state of the art is in the underground. Okay, now we're going to go over Unix file systems. Unix file systems are basically fairly standard regardless of what they're called. So ext2, ext3, FFS, UFS, and so on, all share the same common format. The way that we're going to approach them is going to look at essentially the main components which make up a file system. So a brief holistic overview, and we're going to look at the superblock, which acts as a header to the file system, the data blocks, which do the storage, inodes, which actually make up the files, and then directory files, which organize everything. So this is essentially what your Unix file system looks like. It's one big green blob. At the front, we've got the superblock, which is, as I said earlier, it's a header. It describes the information about the file system. Following that, we're going to have the inode table. The inode table is an array of inodes. So when we talk about inode numbers, such as inode number 1 or inode 3 or whatever, what we actually mean is an index into this inode table. Similarly, we've got a data block table which follows that. And when we talk about block pointers or block numbers, what we mean is an index into this array of data blocks. So that's it. That's essentially all your file system looks like. It's very, very simple. But when we look at a file system, what we're actually looking at is two core things, two main things. It's data and metadata. Just about everything on a file system is about data and metadata. So if we look at, for instance, just files, right, your standard user files, even those are made up of data and metadata. So the metadata will be information about the file, such as the owner, the size, the group IDs, the timestamps, and so on and so forth. This is information just about the file. And then we'll actually have the data itself, the contents that you would be familiar with. Following actual files that you can see, most file systems are actually made up also of what's called metadata files. These are files which contain information about the file system itself, so that someone, so basically the kernel, is able to locate the user files or manipulate them or allocate blocks or whatever. So that's what you got, data and metadata. This becomes important as we go into further attacks on the file system. Okay, the superblock, right? This has to be at a fixed known location in the file system. This is the only thing that you actually have to be able to pinpoint specifically when you start out. As I said, it's a header to the file system. It contains all of the information, such as the number of data blocks, the number of inodes, the location of the inode table, the location of the data block table, and so on. Once we find this, we can calculate where everything else is. Generally, everything else is at a very predictable address rather than being dynamic per file system. However, this has to be at a fixed location. The next part, basically, of a file system after the superblock is the basic data block. This is the lowest atomic addressable part of a file system. So this is the smallest piece of information you can access on a file system. And they're usually fairly big these days, about 4K, 8K. Usually people don't bother going down to 1K or 2K anymore. Data blocks are very, very simple. There are a number of sectors that have been globbed together and just treated as one offset that can be accessed. If you hear people talking about sectors, they're typically talking about the FAT file system. Data blocks is a Unix file system, and clusters is the NTFS word for a data block. Yeah, they're not very exciting. They store data. That's about all there is to it. We start getting into more interesting stuff now. Inodes are basically what make up files. So when we talk about files on the file system, we're actually talking about inodes. Inodes are, as I said, offsets into an inode table. They're just simple data structures, and they contain a bunch of information about how we're going to treat the file. So they basically just contain, as we said before, things like the group ID, the user ID. Let's see, we've got size up there, block count, that's the number of blocks which have been allocated to this file, and a block pointer array, which is used to address the actual file. We'll talk about that in a second. The other thing up there that's important is the links count. Now, the links count indicates the number of times that this particular inode is referenced from within the directory structure. Every time you create a link to a file, that number gets incremented. When you delete a file or you unlink it, that number gets decremented. When it reaches 0, it means that there is no way of addressing this inode using the directory structure. Or in other words, this inode has been deleted from the user visible file system. And that's exactly how things are deleted. What happens when this gets to 0 and the links count is set to 0, all of the blocks which have been allocated to this inode are marked as available, so they can be reallocated and used in separate files. The inode itself is marked as available, so it itself could be reallocated. And occasionally there'll be something called a delete time, which will be set. But generally speaking, that's about it. All of the stuff that's there is just made available for reuse. It's all still available for someone who has a forensics tool to come by and analyze. I said we're going to talk about how block pointers work. Essentially, this is what we have. We've got direct block pointers. These are addresses of data blocks which just store immediate data that you can access directly. And there'll be a limited number of those, say 10. Then the next offset in the array will be what's called an indirect block pointer. This points to a block that contains additional addresses which act as direct data blocks. So we just read on through there, iterating through as if we were accessing just the direct array. Then there's something called the doubly indirect block, which contains a list of block pointers which hold indirect blocks. And then there's the trebly indirect block, which points to doubly indirect blocks, to indirect blocks, to direct blocks. So it's actually all fairly simple once you get a visualization of it. You just trace through it. But once we've got inodes, we now have a way of accessing these blocks and treating them as a stream of data. Unfortunately, we're not very good at remembering things like 32079 as etc password. So there is a system for associating names with inode numbers. That's the directory file. The directory file is just a special format file that's treated by the operating system directly. It contains these directory entries. The directory entries are basically, as before, simple data structures. They're made up of an inode number and a name. So you can go through and you can read the name, and from that you can figure out the inode number, and then you can access the inode directly. There's a little bit of metadata information about the directory entry itself, such as the length of the entry and the length of the name, because these names are actually not null terminated. Let's see. Okay, so when we delete a file, when we go through and we remove a link count, what we're also doing is we're removing the directory entry from being able to reference that file. So we end up with something like this. Basically, a directory file is made up of these entries, which we have over here, and we've got these clearly visible red arrows to indicate where the next directory entry starts. So we would iterate through these entries by using the record length to locate the next entry. So we'd start out at lost and found. We'd get a record length of 16. We'd increment. That would get us to lame file, which would give us, once again, 16. We increment. We get to some file. This one is interesting because it's 32, right? So we increment over this deleted file entry. We can actually no longer see it. It's not visible to the kernel. And at the end, the last file actually has to come up to a solid block boundary. This becomes important when we get to some of the attacks that we're going to talk about later. But as you can see, it's all very clear. Green, red, white, done. So that's it. You're all Unix file system experts. We all know that we've got a super block, we've got data blocks, we've got inodes, and we've got directory files. They're all really, really simple to understand. Inodes are files, data blocks store data, a super block is a header, and directory files act as a DNS system. We're done. All right, now we're going to look at forensics from the point of view of an anti-forensics attacker. So we're not actually going to look at the methodologies that are employed or the specific tools just yet. What we're rather going to look at is the core actions that a forensics officer needs to go through. In particular, we're going to look at data recovery. They actually have to get some data off the device, and they have to do something with it. They have to parse that data, so they take just a blob, and they convert it into something that they can understand. And then they have to perform analysis on that. So they need to take all that stuff that they've now extracted via the parsing phase, and they need to figure out whether they can use it as evidence or whether it's directly related or not. So this is our basics forensics food chain. We start out with a bitstream at the one end, and this is just a straight data dump. We then convert that into a file system. From that, we can extract files, and then when we look at our files, we get our evidence. So our first stage is data recovery. We need to be able to take a blob of data and do something to it. There's several different tools out there that people will use. These are actually starting to databit right now. They've been bundled together and are now available as the sleuth kit rather than as TCT and TCT utils. TCT was the first Unix-specific forensics software kit. It's very badly written, as is the sleuth kit. Basically, it allowed you to recover deleted files and not much else. It's not particularly interesting. TCT utils allowed you to analyze directory entries. Once again, not particularly interesting. What these tools are supposed to provide is something I call total file system awareness. They're supposed to know more about the file system than the kernel or any other tool out there. They're supposed to have complete understanding and be able to do all sorts of really, really cool, exciting things. They don't. They're pretty much crap. So using these tools, what we would do is we would convert our bitstream into a file system, and we'd go ahead and we'd pull out files, which would be, once again, individual bit streams. So we wouldn't really know what we were looking at. We'd just be able to get a blob of data once again. At that point, we would have to try and figure out whether we were looking at a JPEG, for instance, a child pornography CP picture, whether we were looking at email, which might be used in a corporate case, whether we were looking at a document. Once again, it might be a corporate case. Perhaps someone had exceeded their authority in a military situation, had access to documents they shouldn't have access to. Various different things, or ELF binaries, as is popular with the honeypot people. They like to get binaries and reverse engineer them and get ODE that way. So once we've got a file, we need to figure out what it is. And then once we've figured out what it is, we have to be able to do something with it. So this is the last stage that comes along. And yeah, this is essentially the evidence phase. So once we've got all these bits of data, we need to be able to prosecute someone, typically. Or we need to be able to figure out who did something, or we need to come to some greater understanding. That's essentially it. Keyword searches basically fall into this phase as well. This is something that's fairly common, once again, within the corporate arena. They like to find out if people have access to code names that they shouldn't have and so on, so they'll just grep the entire file system. Not particularly technical. And that's forensics. There's not a lot to it. It's data recovery, getting all the data back, data parsing, figuring out what you're looking at, and then data analysis, trying to take what you're looking at and use it against someone for a specific purpose. The core assumption to remember with most forensic analysis is that it basically assumes that the file system is an accurate log of everything that's happened on the system. As we're about to see, that's not the case. Like any log file, we can edit it and we can insert or remove whatever we want. So now we come to anti-forensics. Anti-forensics I define basically as attempting to limit the quantity and quality of forensic evidence. And I've been doing this since 1999. When we're talking about anti-forensics, the important thing that we need to remember is that data is evidence. Everything that we leave behind and everything that we remove leaves data. And that data can be used as evidence towards some purpose. So what we're going to be looking at is ways that we can minimize the amount of data that's available out there to someone who might be coming through and performing forensic analysis. We're going to look at the 3 core principles that I've developed for any anti-forensics attack. Basically, these are data destruction, data hiding, and data contraception. Data destruction is, we destroy the data. Data hiding is we hide the data. And data contraception is where we try to prevent the data from being created in the first place. So we do things to minimize our interaction with the file system. We're going to go through each of these in turn. We'll start with data destruction. Essentially, when we're looking at data destruction, the things that we're most interested in are getting rid of deleted file residue. So once we delete a file, as we saw earlier, all that basically happens is the resources that we allocated for that file, such as the data blocks and the inode, get returned to the file system for reuse. These days, given the size of the average file system, it's very, very unlikely that any of that stuff is actually going to be reused within a few years. So we're worried about the fact that anyone can come along and simply by looking directly at the file system, they can find all of the resources which were allocated and then modified by us and then just left there. So we're going to want to get rid of that. And that means we need to get rid of the dirty inodes, we need to get rid of the dirty directory entries, and the dirty data blocks. So these are all of the places where information will be stored. Then we're going to sometimes want to go through and reset the file system timestamps. So this will happen if, for instance, we go through and we Trojan some system files, or we alter file system headers or binaries or whatever, or we access things that we shouldn't access. We're going to want to reset all of those timestamps back to prior to our entry. So this will also happen. We destroy that sort of data. I developed a toolkit to prove that this could be done and that it was effective. Essentially, there was a toolkit called TDT, the Defilers Toolkit. It was made up of 2 programs. The first program is Necrofile. Necrofile would go through and it would search the entire file system for inodes which had been allocated and then freed. So these would be deleted inodes that you could then go through and we would just overwrite them with zeros. So the content would be erased and they would look as if they were virgin inodes that had never been used to create files. The other one that I wrote was called Clismophile. Brief note, necrophile, as you know, necrophilia is someone who loves corpses. Clismophilia is someone who likes shit, basically. So you can look at Clismophile as cleaning the shit out of directories. It would basically go through and it would look for deleted directory entries and reset them to 0, so that there wouldn't be any file names or any information left over that someone could then come through and figure out that, rootkit.targz was downloaded and then deleted at some point in time. I now do a demonstration. Well, in theory, I do a demonstration. This is where you get to see that the Defilers Toolkit doesn't work when you erase data. So moving right along. The next thing that we're going to look at is data hiding. Data hiding is a lot more interesting than data destruction. Data destruction is actually fairly simple to do once you know what you're trying to do. You just need to figure out what to look at and what to remove. It's possible to do this, to do data destruction attacks on NTFS as well, only it's a lot more difficult because NTFS does all this crap dynamically, whereas Unix file systems are static. So, for those in the audience who care. Okay, data hiding. Basically, when you're hiding data, you want to aspire to subtlety. That means that you want to do things so subtly that people won't notice that there's something there. That's basically all you're trying to do. The format for this section is basically we're going to go over the requirements for what makes a good data hiding attack. We're going to look at a methodology which I've developed for putting together data hiding attacks on just about any file system, although the specific ones we'll be looking at here are ext2. Then we're going to look at several implementations. This is different techniques that I've come up with for implementing this methodology. And yeah, finally, once again, we'll have demos, just like we had last time. Okay, the requirements for a good data hiding attack are very, very simple. The number one requirement is it needs to be covert. It actually does need to be hidden. If it's not hidden, it's not a data hiding attack. There's people I know out there who think that a very, very clever attack is to put a dot in front of the name, and therefore it doesn't appear in the ls output. Obviously, that's a bit crap. The next one that we need to look at is we want it to be outside the scope of a forensics tool. So when someone comes through and uses a forensics tool to examine this file system, we want our data to be hidden beyond where they can actually look. This means that we need to find a bug in the forensics tool that we can exploit to create an area that's invisible, basically, as far as the forensics analysis is concerned. Obviously, the problem with any bug is they're very short-lived. Although in this case, I've been talking about these attacks for well over a year now, and no one's bothered to fix any of their tools. So it's basically like the very old days of security where you can find a bug and no one cares. Yeah, so if you want to use these attacks for long-term storage, you need to be concerned that within a year or 2 years or some amount of time, that bug is going to get fixed, and that area will no longer be invisible to the forensics analyst. The other thing is you actually want this attack to be reliable. You want to be able to put data in and take data out. So, for instance, one attack that sometimes gets performed is people will take a whole bunch of unallocated data blocks. They will remember those numbers, and they will just store data into that. The problem with that, of course, is that during runtime, it's possible that those specific data blocks will be allocated and used in another file, in which case you lose your data. If you want to lose your data, you may as well just use a data destruction attack in the first place, rather than an unreliable data hiding attack. The last one, of course, is we need it to be secure. When we put our data in, we don't want someone else to be able to take our data out and examine it, which is why we're hiding it in the first place. And because we're not stupid, we're going to use encryption. So even though you go through the effort of finding bugs and developing all this software that's going to be obscure and very difficult for someone to put back together what was going on, we encrypt it anyway, because even if they manage to capture our binaries or our processes or something like that, we're still going to be able to keep some part of that safe. All right, this is the methodology that I've developed. Ladies and gentlemen, I'm here to talk about fisting. Fisting is the file system insertion and subversion technique. Fisting is basically taking data and stuffing it where it doesn't belong. So what we're going to do is we're going to look for a hole somewhere in the file system and insert a massive amount of data. Essentially what this means is we use data storage in metadata files. So we find parts of the file system that should be used primarily for storage of metadata about the actual file system, and instead we use that space to store our own data. You can do this just about anywhere. So you can use journal files on journal-assisted file systems. You can use directory files on Windows boxes. You can use OLE2 files, which are documents and so forth. They're actually a mini file system. You can use just about anything on the file system. Unfortunately, of course, when you're modifying metadata, it's very, very dangerous. You stand a good chance of actually destroying the file system, and that's very, very noticeable. So that basically defeats our aspire to subtlety thing. So we need to be quite careful about how we do this, and the rule of thumb is obey the FISC. Right? You need to be aware of what the file system check is going to do. You need to be concerned about making sure that none of the modifications you do step outside the boundaries of those checks that it will perform. So right now you're probably asking yourself, what holes can I fist? Well, if we take this as meaning the entire file system specification, anything within this green area is legitimate as far as the file system is concerned. We can then look at FSCK. FSCK is going to implement a fairly large part of that specification, and is going to be fairly exact in how it does it. We would then have a forensics tool, which would implement some portion of what FSCK does, and also some additional stuff, for instance, looking at deleted data. And then we would have the kernel, which will once again implement a portion of what FSCK does, but also at the same time some additional stuff, such as the ability to allocate inodes or data blocks or modify the file system during runtime. But as you can probably notice, there's holes. You can fist these holes. So if we look at the implementations, which I put together over the past few years, there's 4 that we're going to talk about. The first one is called runefs, which basically uses the bad blocks inode for data storage. The next one is waffenfs, which uses the journal for file system storage. We've got kyfs, which uses directory files. And finally, datamulefs, which uses reserved space within the file system. This one essentially, this runefs attack essentially exploited a very, very cool bug in TCT. Basically, TCT had a check in their code. That's the coroner's toolkit, had a check in their code to find out if a inode number was valid. And that check was, is this inode below the root inode? Unfortunately, they made the mistake of assuming that the root inode was the very first inode in the file system. The way that the file system is put together, you cannot use inode 0 because within the kernel, a 0 inode is used as an error indication. So if you do inode allocation and it returns 0, it's failed. Then they had inode number 1, which was used to store bad data blocks. So what would happen is during runtime, if they discover a bad sector, the block which that sector occupied would be linked to the bad blocks inode, and it then wouldn't be allocated and used in a normal data file as an attempt to mitigate data loss through bad sectors. So this was inode number 1. Then the next inode after that, inode number 2, was the root inode of the file system. So this was the / directory. Of course, as you can see, 1 is less than 2, so we would error out of that TCT check when it came up. The way this was implemented, you only got about 4 gigabytes of storage, which is absolutely huge, but it's still a bit of a limitation. This is essentially what their code looked like. They had if inode number is less than root inode or greater than the last inode, return bad inode. At this point, I do a demonstration to once again show how lame TCT is and how you could cause it to basically not be able to even find the inode, which had our data stored on it. It's just bad balance checking. They fixed it. It took them 9 months to fix this bug. So that brings us to waffenfs. Waffenfs is our first sort of real fisting attack. With waffenfs, what we do is we exploit the fact that ext2 and ext3 are essentially the same file system. The only difference is that with ext3, there's the presence of a journal. A journal just basically stores the state of the file system so that if your computer crashes, you can quickly restore any lost data and so on. The issue is that FSCK, the same program, can check both file systems, but it cannot tell which one you're treating it as during runtime. So for instance, if we use ext2 during runtime, but we have an ext3 journal file, then there's no way that the FSCK program will know that it shouldn't accept the journal file as being valid. So all that we do is we create a journal file on an ext2 file system. It's very simple. It's brain dead obvious. By simply creating a journal file, we can cause the kernel to allocate space for us that we can then use for whatever we like. In this case, we get 32 megabytes of storage. What you'll frequently see with forensics tools is they'll claim to support both ext2 and ext3. They say this because essentially it is the same underlying file system. The problem is that they don't actually support ext3, which would be the journal file. They only support ext2. So whenever you see something that claims to support ext3, it's lying. As a result, we can use this attack to bypass forensics tools. We do this by simply creating a fake journal. So we create the metadata structures that we need in order for our journal to appear valid. That's a journal header and at least one journal entry. Once we do that, we can pass through our FSCK check, which will try and read the journal and replay it until it runs out of valid journal entries. And from then on, we just implement it straightforward as a file. It's quite easy to do. KYFS, kill your file system. This one's quite cool. Basically what we do is we create empty directory entries which occupy an entire block of space, and we can store any data we like within them because they're going to be invisible to the actual file system. This exploits bugs basically with the kernel, FSCK, and forensics tools. So you find problems with absolutely everything with this one. And the beauty of it is that the storage space is limited only by disk size. So we can use as much space as we like. Basically what happens is during the analysis phase of a directory, it's being parsed by either FSCK or the kernel. They're going to ignore deleted journal entry. They're going to ignore deleted directory entries. So deleted directory entries will have an inode value of 0. When an inode value is set to 0, it's supposed to be invisible, so it'll be ignored. So that allows us to simply create a directory entry with an inode value of 0 and a record length of 1 block, and it will be iterated over with this simple code. Forensics tools, on the other hand, are quite interested in deleted directory entries. However, they will have a check that looks like this. So they'll make sure that the inode value is 0, and then they'll check that the name length actually exists. So no points for figuring out how we bypass that check. The last one that we're going to look at is data mule FS. This is basically in the sense of a drug mule. So what we do is we find reserved space or padding space, and we force it to accept data, and then we can extract that data later on when we want it. It's quite useful in that the reserved space is untouched by any tool out there. So neither the kernel nor FSCK nor any forensics tools are going to attempt to look at the reserved space. They're interested primarily in the space that gets used during actual runtime. So they'll look at the owner ID and the group ID and all the other metadata that actually exists rather than the data which doesn't exist. And because it's all ignored, you can put anything that you like in there and no one's going to notice it. Unfortunately, using reserved space limits you to some degree to just how much area there is. There's only so much space in all of this. So if we look at that, within a super block on ext2, we'll have 759 bytes of space. Within a group descriptor, which is something we didn't cover, but it's basically a mini version of the super block that's used simply for optimizations, we'll have 14 bytes. We've got an inode, which is only 10 bytes. And if we look at that for the average file system, so this is per 1 gigabyte with standard ext2 stuff, we end up with 8 groups, which gives us 4 super blocks. Every other group has a backup. So that's about 3K. Group descriptors overall don't even give us 1K. But the inodes, we get over a megabyte of space in this reserved area that we can store any data we like. So for every gigabyte of file system that we have with ext2, we've got over 1 megabyte of reserved space that we can use for arbitrary data storage. Which brings us to the last principle of anti-forensics. This is data contraception. So what is the act of not creating? Right? The theory behind a data contraception attack is very, very simple. It's a lot better not to create data on the disk in the first place than to try and hide it or destroy it or get rid of it in some way. It's a lot safer for it never to be there. So what we're trying to do is we're trying to reduce the quantity and quality of the evidence. So one of the ways that we reduce the quality is by using existing tools on the system rather than implementing and using specific tools that we've put together ourselves. So we'll use awk and sed and sh rather than a program that we've written ourselves in C and compiled into a binary. When we reduce the quantity of evidence, we're looking at things like keeping all of our data off the file system so we don't upload anything that we don't have to. And we'll use something called an IUD to interact with memory space so that we can execute programs without having to upload binaries beforehand. So that's essentially the core principles that we're looking at with this. Non-evident rootkits. This is not new stuff. People have been doing this for quite a while. They've been doing patching directly into kernel memory rather than uploading LKMs directly. Patching SSHD on the fly to do some sort of sniffing, such as password logging or whatever. patches to Apache on the fly, once again, in memory, which can convert Apache into a backdoor that you can access just over HTTPD. All of these things are not new. I mean, there's programs out there to do log erasing based on simple versions of grep and so on. So this has been going on for quite a while. No one's just come up with a cool name like I did. So if we look at one of the attacks that we can do using a standard tool rather than something we've written ourselves, here we have grugq being used to create a backdoor. So you can use this code and it will open port 8080 and it will listen for commands, execute them, and then return the data back over that file descriptor. And yeah, you can get the code off of this. It's quite easy to do. Interestingly enough, some guys in Sweden actually use this code, or code similar to this, in their standard shell code, so that they can have connect-back shell code written with awk rather than having to go through the pain of actually having to do it in assembly. All right, evidence prophylactics. Basically, these are tools that we can use to keep our data off the file system. So it insulates us against getting any sort of dirty residue of any sort on the file system. We use an IUD. This is either an inter or an intra userland device. It provides either as an inter access to its own memory space or an intra access to someone else's memory space. So it's a tool that we can interact with directly that will allow us to manipulate memory on a remote machine. The core guys call this process puppeteering, or syscall proxying is another word that they've used for it. It basically allows you to execute system calls or manipulate memory on another box without ever actually having to upload anything. Unfortunately, you do need an IUD to be uploaded first, and there's several different ways you can get one up there. For instance, you could write your own, or you could exploit a process and use shellcode, or you could go ahead and use a common tool. So people that have written shellcode to use exploited processes are Mostef, which is something that the Immunify guys use, or ImmunitySec, and Core Impact does process puppeteering directly via exploited programs. I've implemented this using a common Unix tool, which would be GDB, the GNU debugger. This allows you to interact with the process using a text-based protocol and to basically manipulate its memory and its registers and so on. I've encapsulated this in a library called libgdbrpc for remote procedure call. It basically allows you to execute system calls in a slave process, and the more interesting ones are, of course, memory manipulation and so on. So once we've got access to a slave process and we've got access to its memory, we can do things such as allocate memory, map the existing binary down, map up a new binary, and execute it from there. It is text-based, unfortunately, which makes it a bit slow, but on the other hand, it means that you can run it over just about anything, like telnet and netcat sessions via SSH through like reverse proxies and so forth, until you actually get where you're trying to get to. There have been actually quite a few implementations of this sort of attack. I'm only going to look at 4 because I can. There's rexec version 1, which is the first version that I implemented of this. There's userland exec, which is basically code which allows you to execute a binary without having to use the exec VE system call. There's ftrans, which was released by the fracI Council, which is basically just code that allows you to upload a binary and execute it using userland exec. rexec v2, which was the latest and last version, which I released of rexec, which allows you to execute a binary remotely without having to create a file on disk. And XSH, which encapsulates rexec and allows you to incorporate it into your standard penetration testing toolkit. rexec v1 was written entirely in expect. It took about 8 hours because I had to figure out how to write expect at the same time. It interacts very, very directly with GDB, which makes it quite ugly for modification and so on. One of the cool things that this does allow you to do is it solves the bootstrapping issue. So for instance, if you've got a data hiding attack for a particular box, the last thing you want to do is upload the binary that you use to access that data onto the box and leave it there in plain sight, visible to anyone. So you can use attacks such as this to execute your tool and be able to access the data without creating a copy of that binary anywhere except in memory. So that's quite cool. It means that if someone's running a honeypot, they can capture less data because you're not leaving anything behind.
You say that it doesn't appear anywhere on disk, but what about the chance of it ending up on the swap?
Yeah, the question is, like, if it doesn't end up anywhere on disk, what about it getting swapped out of memory and ending up in the swap partition or the swap file? There's actually, if you've got root privileges, which is what you'd need anyway to do most of these attacks, or you wouldn't bother having access to the box, there's a system called mlock, or memory lock, which locks regions of memory directly into RAM, and it doesn't allow it to be swapped out. So this actually uses mlock to lock all of the text sections and the data sections into memory directly. Okay. Yeah, so as I said, this reduces the effectiveness of honeypots, which is quite cool. Userland exec, it's basically just a library. It's very small. You can actually incorporate it directly into shellcode, and it allows you to execute an arbitrary ELF binary with your standard like int argc, char star star argv parameters, and run that directly from memory. So it'll map down the existing process, map up your new ELF binary, load the dynamic linker, set everything up, and let it go. I released this basically in January of this year, and within 14 days they came out with this, which was the first code to use it that was publicly available. I was a bit surprised at the speed with which they came out with it. Basically, they developed a proprietary IUD, which used an SSL connection between the server, which was running on the hacked box, and the client, which was running on the hacker's box. And once you had that SSL connection, it would just upload a binary, and then it would call userland exec on that. It was very, very crude. You could tell they didn't write it in a lot of time. They used like SIGINT and other like ugly hacks. The problem with this, of course, is you end up having to leave a proprietary server around, so someone can tell that you've used this sort of attack against them. They called this anti-honeypot technology, which it is. A honeypot is just a very, very extreme forensics environment. I wouldn't bother going that far. I just call it an anti-forensics attack. rexec v2 I released this summer at RuxCon. It basically uses libgdbrpc and libuserlandexec and combines the two so that you can essentially pass it a file descriptor which connects to a shell, pass it the path name to a file, arguments, and it'll execute it remotely. This is really cool. You can basically get a telnet session on anything, and using XSH in this code, you can run any binary you like without it ever appearing on disk. It's brilliant. XSH was code that I used to encapsulate this stuff because basically it's very, very ugly to try and use it any other way. XSH is essentially a hacked up version of Screen. So you fire up an XSH session, you start your own hacking session, and as soon as you get a shell prompt of any sort that you want to use, you can then pop into XSH and you can access things such as rexec v2. You can use ASCII upload. This is when you just want to upload a binary directly over the existing connection that you have, but you don't want to have anything on the remote end to unlock or decode that with. So for instance, rather than using UU decode and VI sessions and so forth, you can just use this directly. It allows something that I call scriptless scripting. This allows you to run script files on a remote host without uploading the script. This is quite useful in a anti-forensics attack, of course, because you don't leave any evidence behind. Once that script interpreter gets killed, it disappears from memory, and there's no evidence that the script was ever uploaded. And command aliases, which just allowed you to collect a whole bunch of commands together and store it over here on your own machine, so you could execute them at any point. And that covers it. That's anti-forensics. Yeah, well, the data contraception summary. Basically, we use IUDs to interact with memory rather than uploading binaries directly. We do what we can to minimize disk activity at all points or access to the file system. it's one of the few areas of anti-forensics where there's actually quite a lot of research being done by other people aside from myself. So all of the PhD guys are quite interested in this stuff, and they're trying to come up with different ways of preventing any evidence from appearing on disk. Let's see. Yeah, people always ask, what about buffer overflows and encase or other specific forensics tools create evidence when you've just gone to so much systems are put together? They tend to be fairly static rather than like all sorts of crazy string copies and so forth. All right, this one's a bit more interesting. You can actually exploit the forensics analyst rather than the forensics process or the forensics tools. So typically in the UK, for instance, a police investigator will have 16 hours to conduct an investigation. That's 2 8-hour days. If you come up with an attack that takes 17 hours to detect, you win. Right? Spend the first 16 hours, they find nothing. They have to move on to the next thing. They've got a huge workload that they have to get through. They can't take the time out to really go after you. Unfortunately, the downside to this is if you get someone who does have 3 days rather than just 2, you're going to get caught. So it's always a lot safer to assume that you're up against someone with a fair amount of time and with a fair level of competency. So you don't assume that the guy's an idiot with like 15 minutes to go over it. You assume that the guy's an FBI agent who's been training this for years and has several months. All right, so that's it. Basically, we've gone over Unix file systems, as we all remember, superblock, data block, inodes, directory files. We've looked at an overview of forensics from the point of view of a forensics attacker, which is data recovery, data parsing, and data analysis. We presented the principles of anti-forensics, data destruction, data hiding, data contraception, and finally, we've owned your file system. So, any questions?
I actually have another question. When you upload a binary via your BGP attack, and you first, I presume that you're uploading a binary that's connected that has shared libraries.
Mm-hmm.
When that linker actually goes and grabs those libraries, you're actually going to touch those libraries, and you're going to leave evidence there.
Yep.
Somebody's going to know which libraries you loaded up.
Yeah, now there is that, but you don't necessarily have to upload a dynamic. If you could load a static one. So I know people who, when they use this sort of attack, don't upload anything dynamic. They've got their entire environments built statically with their own they've actually developed a library format that they use internally. So people are aware of that. However, libraries get accessed very, very rapidly. So for instance, if you use libc, the first time someone runs ls, bang, it gets touched again. And you don't need to worry about that. If you use something very obscure that's never been touched in system installation, that of course would be a bit of a red flag. But generally speaking, I don't worry about that too much. Yeah, the question was if you use the rexec v2 attack and you upload a binary which uses libraries, the libraries will be accessed and loaded into memory, and that will change the access time. So someone could come through and find out, for instance, that libc or libz or whatever was loaded into memory at some point in time, and that could be used as evidence for a program running. Anything else?